We have two talks. The first speaker is Ji Zhu from University of Basel. He will talk about the title is a bit changed. Quantum computing on the racetracks with the flying domain of qubit. Let's write something. Yeah.
Thanks for the introduction, and also thanks the organizers for having me here give this talk and at such a nice conference. So today I will talk about our recent proposal on the quantum computing on magnetic racetrack with flying domain qubits. So this work is done with Stefano, Elena, and Daniel from Basel, and also our experimental friends. Balabir Stuart from Max Planck Institute. Okay, so here's the outline of my talk. So first, I will very briefly mention the background, and then I will move on and define what is the domain qubits, and then I will show you how can we shuttle this domain qubit on a magnetic racetrack within this, basically within a nanowire. And how can we implement this single qubit rotations and two-qubit gates by simply controlling the motion of the domain wall on the racetrack. And finally, I will discuss this qubit readout and also its life. So let's start with the background. It is nice that Oleg yesterday already gave a very nice introduction on this ferromagnetic domain wall. So I just very briefly go through this part. So the main role is basically a magnetic domain wall. Imagine we have a magnetic nanowire, and on the one hand, as we sketched here, on the one end, let's say all the spins are put up, and on the other end, we have all the spins put down. Then the spins in between, they will smoothly connect these two domains. Like one way to do is as with what we sketched here. And there's one important parameter, basically it's the domain wall width. We denote as lambda here. So there are many important applications of this kind of domain wall in spintronics. And one of them is so-called the racetrack memory, which is proposed by Stuart a long time ago, where we basically use this kind of classical domain wall as a classical qubit to store the, classical bit to store the information. And after this, there are a lot of experimental efforts along this line. And now we can really move and manipulate the domain wall within the nanowire, or what we call the magnetic racetrack, very easily, for example, by applying magnetic fields or electric current. And amazingly, now people can really move this kind of domain wall on antiferro or ferromagnetic racetrack with a super fast speed. For example, it can be even larger than 1 kilometer per second.
Just a simple. Is it important that you have a near domain wall or block?
Yes, a near domain wall.
Block or blocks are not good here.
Sorry?
Block domain walls are not good in this context, though.
I mean, of course, you can have a block domain with.
So it's not important.
It's not important.
Just look at the slide and so made.
Okay, yeah, it's not important. It's just an example.
Oh, okay.
For some reason, Stuart likes it.
Yeah, anyway, so all these achievements so far, they're amazing. And the question we try to ask is, can we really go beyond this picture? And one natural answer to this is, just to push, can we push all the system, into the quantum regime and ask if we can use this kind of domain wall, for example, for quantum bits and use for quantum information processing, for example, for quantum computing or quantum communication. So, yeah, to really use this domain wall as a qubit, the first question we should really ask ourselves is which degree of freedom we want to use to store this quantum information. So before I dig into the details, I just give you a very rough idea. So what we propose is to use the chirality of the domain wall to store the quantum information. So for this kind of chirality, like what we sketched here for this upper panel, you can see, let's say we have all the spins on one end, on this left end, they all point downwards, and the other end they point upwards. Then there are several different ways to connect these two domains. For example, one way is to rotate the spin from down to up, counterclockwise. And if we move all the spins onto this spin space or all the parameter space, then that would correspond to this right trajectory, right? So first we have this spin point downward, and we rotate it counterclockwise. Eventually, it will arrive at this spin up. So there's another way to connect this. Basically, we also rotate the spin from down to up, but now clockwise, and this would give us this blue trajectory, as we can see here. So we have also spin down, and gradually we rotate it clockwise, and eventually we also arrive at this up state. And as you can see, we call this upper one as a positive chirality state, and the lower one as a negative chirality state. And this state in the order parameter space or spin space, the azimuthal angle is phi equal to 0, and this negative chirality state, the azimuthal angle is phi equal to pi. And the idea is basically to use this chirality with freedom as a pseudo spin, to store the information. So I'll give you more details later.
Excuse me. So I mean, is it like we have a easy planar?
Yeah. I will show you all the details. Of course, you need something to help this. Yes, here I just refresh your memory about this well-known different transfer criteria. So first 5 points, they're basically requirements for a quantum computer, basically saying that we must have a well-defined qubit. We must be able to initialize our state into some well-defined state, and we also must, so this kind of qubit must be also non-lived, and we should also be able to implement, universal set of quantum gates. And finally, of course, we should be able to read it out. And the last 2 points, they are requirements for quantum communication, basically saying that I can convert my stationary qubit to a flying qubit, and from a flying qubit to a stationary qubit. And the second point is saying that when the flying qubit is moving from one point to another, this process must be coherent, and there should be no quantum information loss. So hopefully I will convince you that our proposal is not only good for quantum computing, but also for good quantum communication on the solid state level. Okay, so let's give you this kind of a simple theoretical model. So we consider a rather simple two subnets called the one-dimensional ferromagnet, as we sketched here. So every spin here, you can think of as like two spins pointing in the different direction with different spin lengths. For this kind of system, the dynamics can be described by an antiferromagnetic order, basically the near order, and also a weak ferromagnetic order. And we assume this net spin within the unit cell is SE, basically the difference of the spin lengths. Of course, we can move on and write down this low energy description for such a system. So for example, for the kinetic energy, we basically have two terms. The first one is for the antiferromagnetic part, and the second one is for the ferro. And the physical meaning of each term is also very clear. By the way, this H is the applied magnetic field. So for example, for the first term, if we expand it, we have three terms. The first term is basically n dot square, which is the standard kinetic energy for the antiferromagnet. And the cross term, which is linear in applied magnetic field, and also linear in the time derivative, meaning that it's a geometric phase. This kind of a term describes the fact that when you apply a magnetic field to an antiferromagnet, this applied magnetic field would create a net magnetization, and this net magnetization will accumulate spin barrier phase in the dynamics, and that's this kind of effect is described by this cross term. And the last term, which is simply this given by h cross n square, This is basically the easy plane anisotropy induced by this applied magnetic field. It's just saying when we apply a magnetic field, this new vector would like to be perpendicular to this applied field. So the last term is the standard, Berry phase term for this ferro. And here, as you can see, it's proportional to SE. And also this spin connection, A is defined in the standard way.
No, excuse me, so, okay, so, so you're, the kinetic energy is just referring to time derivative theorem.
Yeah, we have more terms, like you mentioned the anisotropies. Yes, the potential energy, that's some anisotropies. So, well, for this potential energy, we also separate into two terms. For example, this one, the first one basically is the exchange, just saying that the texture must be smooth, right? And this second term here is the easy z axis anisotropy, and we label it as capital KZ. Because of this term, all the spins they want to point, along the z direction to minimize this term, right? And this term, the first term here, is what we call the easy xz plane anisotropy. So because of you can say this ny square. Then all the spins want to stay within this xz plane to minimize this term. And the last term is the standard Zeeman coupling. So here are just some remarks. So first, for this kind of this action, we rescale the spatial parameter x to lambda x, where lambda is basically the width of the domain wall, which is proportional to the square root of exchange divided by the easy axis anisotropy. So basically, we're saying that we measure the distance in the unit of domain wall width. And importantly, we assume this hierarchy of energy scales in this problem. So the largest energy scale is the exchange, which is around room temperature, 300 Kelvin. And then the second largest energy scale is this easy axis anisotropy, it's about 3 Kelvin. And the other energy scales like the easy plane anisotropy and also this Zeeman energy, they are 1 order of magnitude smaller than this KZ. So if we plug this guy into here, then we would conclude that this domain wall width is about 5 nanometers.
Next question. You have 0.1 kelvins for these last interactions, and usually magnetodipole interaction is of the same order of magnitude.
Yeah, I mean your easy.
But you don't consider.
Your easy plan, your dipolar can give us this kind of some anisotropies.
It's part of that.
Yeah, it's part of that.
Okay, so
It's the net
Yeah,
easy X.
exactly.
so it contributes.
Yeah.
Okay.
Okay, so yes. So once we have this kind of energy hierarchy, then we can basically treat the last term here as a perturbation of the first term, right? So to get this kind of domain wall configuration, we just need to minimize the first term with the proper boundary condition. And then we would arrive at this standard domain wall solution. Importantly, there are two zero modes. One is this spatial X, which is basically the spatial location of this domain wall, which is a zero mode because of the translational symmetry in the real space, right? And another zero mode is basically azimuthal angle phi if you only consider the first term. And that's because there's a U1 symmetry in the spin space around the z-axis. Remember that this phi equal to 0 is this positive chirality state, and phi equal to pi gives us this negative chirality state. And of course, if we only consider the first term, then all the angles from 0 to pi, they're all equally preferred. However, when we include this easy axis easy axis plane anisotropy, this guy, as you can see, would break this U1 symmetry to Z2, right? In this case, then this two chirality state, phi equal to 0 and phi equal to pi, they are preferred compared to other possibilities. Okay, so now let us focus on these two soft modes. We can write down the effective action for these two soft modes. So the first line is for this azimuth angle phi. The second line is for the spatial coordinate. And the last line is basically the interaction for the coupling between this real space and spin space. So as you can see, this first term here is basically the standard kinetic energy. And this term is the easy plane anisotropy. Because of this term, phi equals 0 and phi equals pi, they are preferred. And the second term here is basically the easy plane anisotropy induced by this applied magnetic field. And due with the energy hierarchy that we assumed, this term is much smaller compared to the first term and the last term. So we will drop this term in our later discussion. And the last term here is a standard Zeeman coupling. So the second line is basically the Lagrangian for this spatial X. Here we add a confining potential for this domain wall with a frequency omega p. This last line is the coupling between the real space and spin space due to this spin Berry phase effect. So there are two contributions. One is from this ferro part. That's the last term here, which is proportional to SE. And there's also a second contribution due to the net magnetization that's created by this applied magnetic field. Remember this, when you apply a magnetic field, you create a tiny magnetization that would also accumulate spin Berry phase. That's this first term. And as you can see, it's linear in applied magnetic field. Okay.
Could you please maybe comment more about this confining potential? So when you try to move your domain wall across the x-axis, along the x-axis, you will have some potential wall?
Yeah. Well, later you will see more, but I can say that there are possible ways to do it in the experiment. We also discussed with our experimental friends.
It looks unusual, so yes.
Change the width of something of the strip. I mean, what would be the narrowest place?
Yeah, well, they told us they can do this kind of experiments. Basically, you put one racetrack and another racetrack underneath. There's one domain wall up and another one domain wall in this lower racetrack. This lower one would naturally provide this kind of confining potential. When you move this lower one, it's like you can. They actually have. There are already experiments like this.
Oh, that makes sense.
But of course, not in the class already.
These are big fat skeletons.
Anyway, so very there's one important feature you should notice is that this action is proportional to the size of the domain wall, meaning that if your domain wall texture is larger, then it's more classical. And at this point, it's already not so difficult to imagine that this coherence time or the lifetime of this domain wall qubit would be inversely proportional to this domain wall size. Right? And now let us move on and define this domain. What is the domain wall qubit by focusing on this first part? It's basically the azimuth angle phi. And later, I will utilize this spatial degrees freedom to really implement single and two-qubit gates.
I have a question, a basic question. So your spin is the classical spin.
Yes.
And then you're talking about the
No, you can quantize. It's a two soft
so
modes.
for example, positive chirality domain, negative chirality domain. If you're thinking about the superposition of two, would you get the blocked domain more than?
No, it's different. The probability is still, there is no such a probability in probably basically it's a superposition of this trajectory and this trajectory.
Yeah.
And the block domain wall is like along this this line. It's not like it's a quantum state, and
Yes, that's right.
the probability staying out of plane is still almost there. For the block domain wall, the probability staying out of plane is almost one.
Yeah, it's not one spin, it's many spins. And so it's not simple, Z plus minus C gives you X.
Yeah, it's not quantum, yeah. It's still a superposition state, it's a macroscopic like superposition state. It's kind of like a CAD state, but of course, we really care about the lifetime. If the lifetime is too short, then it's basically a classical domain wall. And
So which means can you make an entangled state then to get?
yeah, I will, of course, that's a part of our task. Otherwise, yes. Thanks for all the questions. Anyway, let's move on. Okay, so let's look at the potential energy. Here we have introduced a two-dimensional magnetic field just for convenience, Bx and By. So let's turn off this Bx, which is first. Basically, there's no applied magnetic field along this racetrack. So we have only the magnetic field in the y direction. So in this case, the potential energy for the azimuthal angle phi is like this kind of double well potential. Remember that this phi equal to 0 is the positive chirality state, and the phi equal to pi. Of course, phi equal to minus pi is there are also this kind of negative chirality states. And for this kind of potential, we know they can tunnel to each other. It's a quantum process. For one way to tunnel is from 0 to pi through this phi equal to pi over 2. That's physically corresponding to this radial trajectory, go all the plan and through this positive y-axis and reach this blue trajectory. And there's another process is process B, which or in this process we go from 0 to minus pi through the negative pi over 2. That means we also for this red trajectory, it also goes out of plane and then through this minus y-axis and reach this blue trajectory. One important point is this magnetic field along the y direction would control the tunneling barrier at this 2 position. The physical, the reason is also clear physically because when you apply a magnetic field along the y direction, then of course when you tunnel, when you go out of plane and it would prefer to go through the positive y-axis because there's some applied magnetic field along that direction. So it just prefer to go to through the positive y direction. That you can see mathematically it corresponds to the fact that this tunneling barrier would be suppressed due to this applied magnetic field, and correspondingly this tunneling barrier would be increased. And okay, so of course, with this kind of profile, this process B, the probability would be much small, exponentially smaller than the process A. So we will just focus on this single double well potential. Okay, so now let's check what's the effect of this magnetic field along the racetrack. Right, so it's actually very clear if you just draw this kind of a positive chirality state and negative chirality state. It's clear that when you apply a magnetic field along the racetrack, for example, along the positive x direction, then this positive chirality state would be preferred compared to this negative chirality state. Right, that means this kind of magnetic field along the racetrack would give us a detuning between these two chirality states. So if we project all the dynamics onto this low energy manifold, these two chirality states, we would get an effective Hamiltonian like this. So first we have this detuning term proportional to sigma z. By the way, it's in the chirality basis. This epsilon is proportional to the applied magnetic field. And of course, there's a tunneling term, which is proportional to sigma x, with the tunneling rate Tj, which is controlled by the tunneling barrier. And very importantly, those two parameters, they are both tunable by external fields. And that's very important. This kind of tunability is important if we really want to use this degrees freedom to store information.
Here you consider only quantum tunneling, not a temperature-induced tunneling. temperature can also help you to tunnel from the
Well, yeah,
the temperature is very small. Eh?
of course. I mean, all this spin qubit like superclass qubit is always mini Kelvin
But you
region.
can estimate the temperature, which is some characteristic temperature for the stomach.
Yeah, you will see that. This kind of definitely you want your tunneling, sorry, your temperature at least to be comparable to your qubit splitting, right? And definitely much smaller than this tunneling barrier. If your temperature is kind of comparable to your tunneling barrier, I think this tunneling barrier is about like probably 10 Kelvin, something like that. Then you don't have any qubits. There's no quantum effect.
So you have an effective spin on the model here.
Yeah.
But these are big fat solid ones. There must be lots of other quantum states nearby. I'm just defining what it means.
You mean what? You mean like magnons or whatever?
No, I mean, just rotating your plane of the domain board.
Yes, that's
There's probably a lot of states there as you do this.
I mean all those kind of stuff goes into this estimation of coherence time.
No, but it's not just the coherence time, because here you think you just have two states of the lowest energy. But as you apply a magnetic field and you raise one of them up, and maybe there are lots of other states in between these two energies.
I mean, this kind of a double well, it determines the lowest energy states, and the next.
So there'll be some harmonic oscillator states there.
Yeah. That determines by this basically the curvature of this well, and that's basically the splitting. You are right. If this guy is kind of compared to this guy, is not a good qubit. That's something we need to guarantee, and that's why we have assumed this kind of energy hierarchy. And also there is a constraint for the size of the domain wall. And yes.
I mean, doesn't that kind of set the minimum possible value we can have for By? Because I mean, if By is, you should not have like multiple.
Exactly. Yes. There's if you suppress it too much, then it's also not a good qubit. There's some constraints for the.
Yeah, I mean, but seems like By should fall in some right range, or I mean, sorry, unless By is. I mean, if By is too large, then it's not cute. You can't even have a qubit, but well, if By is just zero, you may end up.
Yes, you're absolutely correct. So when your By is small, like when it's zero, then there's the tunneling is basically zero, and there's no qubit. And if it's too large, then basically this guy is comparable to this guy. It's not also not a qubit. And the physical with the parameter we have, we estimate that the By, the corresponding magnetic field, should be like hundreds milli-Tesla to 1 Tesla, something like that, or several Tesla. That's definitely one constraint. So we consider that. Yeah, thanks for asking that. Okay. Okay. Yes, here I just show you this kind of the effect of this magnetic field along this racetrack. So if we have a magnetic field along this positive x direction, then we would get a negativity tuning. Then the positive chirality state is preferred, and we can use this way. This as a this is basically a way to initialize a qubit into a certain chirality state. Just of course, with all these expressions, and we have all the numbers for the parameters, then we can estimate, okay, what's the typical qubit splitting, and it turns out about 20 gigahertz. But I should point out that this guy is not really the physical qubit splitting, because remember this as Nielsen angle phi, they are coupled to this real space coordinate. This coupling, as you will see in the next slide, would renormalize our tunneling rate.
When you get the 20 gigahertz difference, what is the special extent of your socket?
Sorry?
Thickness of your domain.
You mean the size of the domain wall?
Yeah.
We assume it's 100 spins in the domain.
100
spins within the.
Because require very fine, so.
Yeah.
What's the distance to the next excited levels?
I think it's like 9 or 10 times larger than this. Yeah, we should make sure that. Otherwise, we need to do like a reverse perturbation and take those states into account, and that would it's a bad qubit. Okay, so yes, now we should consider the complete dynamics. Basically, not only the azimuthal angle phi, but also this spatial coordinate. So just to illustrate the effect of this spatial coordinate, spatial degrees freedom, here I just said there's no applied magnetic field along the x direction. Then if we project this phi dynamics onto this qubit space, then we will just get this tunneling sigma x. And remember that this Lx is basically a harmonic oscillator. So if we then that in the Hamiltonian form, it's basically p squared. Forget about this sigma z first. Just p squared plus x squared. And this x naught is a classical parameter that tells us this position of the domain wall, which generally speaking is a function of time, which is can be controlled externally. And when we project this coupling onto this qubit space, we would get this effective spin orbital coupling, and this beta z. The coupling strings, there are two contributions again, because there are kind of two contributions from the spin barrier phase. One is proportional to the net magnetization, another one is due to the applied magnetic field. Very importantly, here we introduce one important length scale, basically the spin orbital length, which is about 1.5 nanometer. Basically, it's saying that this distance is basically the distance that we need to travel to flip the spin. And to reveal the effect of this domain wall motion and also this spin orbital coupling, it is very natural to put a new frame that is moving together with the domain wall. To do that, we just need to apply this unitary transformation, which is basically a displacement operator in the real space. And that will give us a new term that is proportional to the velocity. And still we have this kind of coupling term. To do that, we apply a gauge transformation, which is basically a spin-dependent displacement in the momentum space. And then we project this dynamics onto the ground state of this orbital dynamics. That eventually would give us this effective Hamiltonian. As you can see, this tunneling rate now is renormalized. Actually, is suppressed by this spin orbital coupling by order of magnitude. Now it's about 3 gigahertz. And we should notice that here we get a new detuning term, which is proportional to the velocity. And the reason why we have such a detuning term, you can think of like when you move your domain wall, you basically explicitly break the inversion symmetry in your real space, and your real space is linked to this spin space through this spin orbital coupling. So you also somehow effectively break this Z2 symmetry in your spin space. You have this sigma Z term. Definitely, there's one important constraint is the maximum velocity that we can move without move our domain wall. We couldn't just move our domain wall with infinite fast speed. Of course, when we move our domain wall with a faster velocity, then we get a higher probability to excite higher energy states. But that's something not we don't want. We just want to stay in the low energy manifold and manage the information. Otherwise, the information would leak into the high excited state, and then it's a bad qubit. And the maximum shuttling distance is about 100 meters per second. Okay, so now we can really plot this our physical qubit energy. So here is of course the qubit energy is basically the square root of the detuning square plus this tunneling rate square. Here we have you can restore this tunneling, this detuning induced by the applied magnetic field along the racetrack. This is a density plot of this qubit energy as a function of the B fields. So one important feature we should notice that it's basically like when we increase the magnetic field along the y direction, so first this qubit energy will increase and then decrease. The reason is worth clear because remember without the magnetic field the battery is very high, then the tunneling is basically zero. There are basically no qubit. So when we increase the magnetic field, the tunneling barrier is suppressed, so we get a larger tunneling rate. That's why we have a larger qubit energy. But when we keep increasing the magnetic field, then we get a larger magnetization that would lead to a larger spin orbital coupling that would suppress this tunneling process. That's why we get a smaller one when this guy is large. And of course, if we want to really have a good qubit, we should only stay in this region in between. We don't want BY to be too small or too large. Okay, now I can tell you how to implement this single qubit gates, single qubit rotations. So there are several ways to do it. The most straightforward way is basically you just move the domain wall with a constant velocity. And naturally, this Hamiltonian would lead to this spin rotation around some axis, m axis. The position of the axis, which is basically tunable because the theta is determined by the ratio of this tunneling rate and versus this detuning. And another way to do it is basically we can just shake this domain wall on the magnetic racetrack. To see that, we can simply assume this velocity has such a profile with magnitude of V0, and this st is just an envelope function. You can assume it to be 1. Just for simplicity, and omega d is some driven frequency, and phi naught is the initial phase. And the resonance is very easy to show that when phi naught, the initial pulse, the phase of this initial pulse is 0. Then we realize a rotation around this x-axis, and when the initial phase is pi over 2, then we get a rotation around the y-axis. So there's one important parameter associated with this kind of gate operation. It's basically the time, gate operational time. And in this case, the gate time is simply given by the spin orbital distance divided by the velocity. Remember, the spin orbital distance is basically the distance we need to travel to flip the spin. So the time is simply given by the distance divided by the velocity. In our case, it's about 0.1 nanosecond. It's pretty fast. Okay, so for two qubit gates, we need to consider two parallel racetracks. Of course, you can also put one racetrack on top of the other, and then naturally they would talk to each other through, for example, dipolar, or if you put it on top of each other, separated by some space in there, then they can talk to each other. So some RTQY type of interaction. And the general interaction form is like this. Here, alpha, beta, they are spin indices. We assume, for example, one domain wall on the upper racetrack, and there's another domain wall on the lower racetrack. Then, we do kind of similar stuff, project the dynamics onto the this qubit subspace. Here we also assume the distance between these two domain walls is capital D, which generally speaking is a function of time. Of course, they can move with different velocity. Then we arrive at this effective interaction between these two qubits, which is basically sigma 1x dot times sigma 2x. And you should notice that this interaction is exponentially small when this d is larger than the domain wall width, meaning that these two domain walls, they can only talk to each other and get entangled when they can see each other. So to illustrate this entangling gate, For example, let's assume the lower one, the domain wall is fixed, and the upper one, we shuttle it with a velocity v. Then we would realize an entangling gate when this prefactor is about is pi over 4. It's basically a C0 gate. And just give you some idea about these parameters, when the interaction is about 50 megahertz, which apparently is achievable in experiment, according to our experimental friends. And when then we need to shuttle the domain wall with the velocity about 20 meters per second. The corresponding gate operational time is about 0.2 nanoseconds. Of course, when we have a stronger interaction between these two domain walls, then they need a next time to get entangled, right? Then we can shuttle this domain wall with a faster velocity. And the gate operational time in this case is simply given by this domain wall width divided by the velocity. How much time I have? I'm almost 5 minutes. Yeah, okay. Yeah. Okay, that's good. I'm almost done. Yeah. Yes. So of course, another thing we care about is this qubit lifetime. If it's too short, then it's just a classical domain wall. To estimate that, of course, the reason why we have this kind of decoherence, and like there are so many quasi-particles around, we have lattice vibration, we have disorders. Those kind of factors would lead to this kind of fluctuation in our two key parameters, the azimuthal angle phi and also this spatial coordinate. You can work out the fluctuation this C by fluctuation dissipation theorem. And this guy is proportional to the alpha, which is basically the Gauss damping, and N is the size of the domain wall. Okay, so the fluctuation in the position of the domain wall would translate into the fluctuation of the velocity. That would give us the this kind of fluctuation term in the detuning. And the fluctuation in this azimuthal angle phi, because of this fluctuation, then this double wave potential, remember, it would oscillate everywhere. And of course, this kind of fluctuation would lead to a fluctuation in the detuning. That is this guy. And also, the tunneling area is also fluctuating. So we would get this fluctuation term. And once we have this kind of fluctuating terms in the qubit Hamiltonian, it is very straightforward to write down the T1 and the T2, or the relaxation rate and the dephasing rate. So one important thing I should point out is this pure dephasing rate, gamma phi, which is proportional to cosine theta. And this cosine theta is proportional to the detuning, meaning that when the detuning is 0, so this magnetic field along the racetrack is balanced with this shuttling speed. Then this guy is 0, and the cosine theta is 0. Then this pure dephasing is 0, and in this case, it's what we call the sweet spot. Because in this case, dephasing rate is minimized, and the T2 is maximized. And here is just a plot to show that here we assume velocity is 0. Then Bx is 0 is basically the sweet spot. In this case, as you can see, this dephasing rate is minimal along this line. And of course, the T1 or the relaxation rate is the maximum along this line is proportional sine theta square. And we know, like generally speaking, this dephasing process is a limiting factor for a qubit. So we really want to minimize this dephasing rate. And this first term here, this first plot here is basically the T1, T2 at different temperatures. Just give you some numbers. So when we shuttle the qubit with velocity 20 meters per second at temperature 50 millikelvin, and the T1, T2 they're about 0.2 microsecond. Another important parameter is this coherent shuttling distance, meaning that it's basically the distance that this domain wall can travel before it decohere. That's about 3 micrometers. It's a large distance, solid state platform. And finally, this quality factor, basically the number of Rabi oscillations that we can realize within the coherence time is about 1,000. Okay, so it's almost okay. Just maybe 1 minute. So last thing is about readout. There are several possible schemes we can use. So one is basically we can use this MV centers basically to take a picture of these textures and see the chirality. Another one, so the whole idea is basically couple our domain wall qubit to some already developed qubit, for example, MV centers or spin qubit or superconducting qubit. Another thing is couple this if our racetrack is conducting, then we can couple this racetrack to some paramagnetic dots. Then this electron can tunnel to this dot and get polarized, and this polarization can be read out. Okay, so finally, I think I have showed you all these points, and the main thing is basically now we have a qubit. We can realize not only in first 5 points, but versus the last 2 points. So it is really a flying qubit. It is mobile, and we can move it coherently for distance in micrometers. And finally, thanks for your attention, and also my collaborators, Stefano, Banabia, Stuart, Elena, and Dan.
I think we can have one more.
Can you tell me how to obtain the Rabi oscillation experimentally in this case?
Yes, that's basically the go back. Okay, that's basically the single qubit rotations. There are 2 ways. Probably the simplest way for you is just to move this domain wall. Like we already had some discussion. One way to do it is like put one racetrack and another classical racetrack underneath, and the domain wall within the classical racetrack would drag this quantum domain wall to move, and to do that. The reason why we do that is because the heating effect, of course. If you just apply directing the current to this quantum domain wall, then the heating will be huge, and unless you have some smart way to suppress the heat.
So the question is what's the big advantages of your domain wall qubit compared to superconducting qubit?
Yes.
It's like you have some kind of magnetic material. There's lots of magnetic effects, something like that. They cause the diffusion time very low, something like that.
Yeah.
This is your theoretical prediction, but I expect you have a very small number of diffusion time compared to other qubits, something like that. Then what is your big advantage?
Okay. I always appreciate this question.
Yeah.
Give me a chance, to see something that I didn't emphasize. First one is just what I said. It's a flying qubit. It's mobile. Superconducting qubit that you mentioned is a stationary qubit. To connect to distant superconducting qubit, you need some external component like resonators or whatever. But here, this kind of flying qubit, they can do it just by themselves, just move, and it's a coherent process. And another thing, back to your point, this kind of coherence time. Yes, I agree. This coherence time is relatively short. By the way, here we use some parameters that are already feasible from their experiment. And it's short, but you should compare with your coherence time with this gate operational time. Namely, if even if, for example, I don't know, like a nuclear qubit or other qubit, the coherence time is super long, like 4 hours, but you also need an hour to implement a qubit gate. Then it's useless, right? Here, even though it's kind of relatively short, it's like a 0.2 microsecond, but the gate operational time is also very short.
Sure. So
Yes.
I understand about about this kinds of defects. You don't know the defects, so
Yes.
the magnetic effect that deteriorate your defacing time or not.
Yeah. Yes, I agree. That's a theoretical proposal. That's what we can do, right? Then we just need to wait for experiments. Yeah, by the way, another advantage is this domain wall stuff can naturally go to 3D. The original proposal of this racetrack is really 3D racetrack memory. Imagine have some like a racetrack like this. That's something difficult for superconducting qubit or spin qubit. Yes, that's some.
Let's thank the speaker.